Okay, thank you, Amanda, BJ, Brian, for the invitation. So I'm going to talk a little bit about distributed sensor networks, and in the end, talk a little bit about the impact on resilience, autonomy. A number of the things in this talk are related to a recent paper that I wrote with one of my former students, Nassar Ahmed, where we actually used, we rolled up a lot of the work we've done over the last 10 to 12 years, and the consistent example was a game of hide and seek or tag with kids. So it's in the control systems magazine. So my focus on distributed information networks or sensor networks, the goals are to exchange information across the network and really try to maintain a consistent estimate of the state. We'll talk a little bit about that at the very end, especially in the impact of resilient autonomy. And then the third goal, depending on the application space, is to try to enable some type of distributed or decision making which could be distributed or decentralized. There's a bunch of applications here. Manufacturing, distributed cars, of course, air traffic control, and so on. So what I'm going to focus today on are these challenges here. And I've kind of grouped them into two areas. One is the complexity of the process and the sensing that you're looking at. So that could be the different kinds of distributions you're looking at, whether your sensor is moving or not, or what kind of sensor it is. For instance, is it vision-based, or is it something a little bit different? And then the associated uncertainties. But then, of course, there's the complexity of the network itself. Okay, there's the topology and whether that's static and what it is and whether it changes. Whether you drop packets, whether you're guaranteed to drop packets or guaranteed to receive all the data. And then the time synchronization is typically very, very important. Certainly, we've seen that in a lot of our sensor fusion work. When you're looking at processes that are dynamic. So the paradigm I'm going to focus on is called the Distributed Data Fusion DDF paradigm. This was first developed by Hugh White in '94 and has been built on in a number of ways by a number of different people. It's a Bayesian approach. And so there's a high-level block diagram here given just to show you what happens. Effectively, sensors collect local data about the process, fuse that information locally, and then there's these filters called channel filters, which are connected to neighbors. And the channel filters really maintain a knowledge of what the common information is between the nodes. Okay, so what that allows you to do is it allows you to collect local information, compare it to the common, send out the new information, and then you get back new information from your neighbors. So it's fairly straightforward. The nice part about this is that it's equivalent to, you can show that it's equivalent to a centralized column filter if you're looking at linear dynamics and a measurement, Gaussian noise, and then a tree topology, which is one of the key assumptions that goes into this. So the benefits are that it's scalable, okay, so you can summarize a lot of the information from your neighbors. It's modular, so you can really build it up in terms of the topologies and so on, and it's robust. So even if there's a link that is broken, there's no centralized point of failure because it's distributed across the entire network. So there's a bunch of different examples, and there's a couple different applications I'm going to use throughout this talk. One of which is a collaborative train height mapping application that we worked on about 10 or 12 years ago. So the approach here is that you have a bunch of robots that need to explore some type of space, and you want to develop a height map. So fairly straightforward. The representation is a grid, and then inside of each cell is a Gaussian distribution of a dominant height. The network is a TCP/IP communication, so you might have drops and outages and so on. And there's many different uncertainties. So consider 8 robots, each with a certain pose, attitude, and sensing. So what you see on the bottom left is the map, and on the bottom right are 8 different trajectories. So this is just a video that shows the view. This is the experimental setup. And you're going to see the data collection and the map being formed over time. Okay, so this is just the view from node or robot number 2 of 8 robots. And you see there's a chain topology, so you see the topology in the upper right. And so over time, the robots communicate. We were able to then collect a lot of data and then study different kinds of things with the network, particularly drops and topologies and so on. And so, so you see the height map being developed, but the interesting plot also is at the bottom here. So in the maroon is the information that you get from the other nodes in the network being collected, and the green is the local information. So over time, you're able to share information, even in the presence of drops and things like that. So I have a couple more plots a little bit later on that talks about this in a little bit more in detail. Okay.
So how do you ensure that the tree topology is maintained, or?
We basically have assignments and sharing knowledge of exactly who is communicating with who. So, but this is certainly one of the limitations. So I'll talk about that sort of. So now what I'm going to do is I'm going to start to go through some more different kinds of complexities. The first one I'm going to focus on is sensor complexity. So what happens in this paradigm as you start to think about dynamics and motions and uncertainties associated with sensors? So a few equations here. So the first is the original DDF paradigm focused on linear systems, of course, so then you can go to nonlinear systems, and there's been a lot of work that showed that you can use a linearized version of DDF. It's in the information filter paradigm, so the performance is similar to what you get from the extended common filter, the single point filter. So I'm not going to talk about that too much, but then the next step would be what happens if you actually have dynamics. So you actually have a moving sensor, so for instance a UAV with a camera on it. So in that case, the state, or the measurement itself, is a function not only of the processing you're measuring, but also the location orientation of the sensor itself. So I've sort of labeled this X superscript S. So there's a lot of different aspects. This is some of the work that we've done over the years. So there's a lot of different aspects that you can focus on this. But one of the approaches that we've been able to do is to marginalize a lot of the local information, because that is not pertinent to what my neighbors are also collecting. And what that does is it creates some type of discount of the information before I actually send it across the network. So I'm going to give show an example here. So this is a cooperative UAV geolocation problem. So the example here is a couple of UAVs. Those UAVs have gimbaling cameras on the inside. They're tracking objects on the ground, which might be cars and people. So it's vision tracking, and this was done roughly about 10 or 12 years ago, so it's fairly simplified vision tracking. But there's a lot of different uncertainties. So there's the pose, attitude of the UAV, there's the gimbaling camera, and so on. And then there's the network has the potential to drop packets in that. Okay, so this is the C-scan UAV, so this is in collaboration with a group called In Situ. So this was the final demonstration where we were doing 30 minutes of tracking of different objects on the ground. So this just shows a couple of different views. In the top left and the top right are the views from the actual UAVs, tracking the moving car on the ground. And the bottom is what the operators were looking at, which is the trajectories and the proposed trajectories of the UAVs. They flew in orbits at different altitudes over the object. Okay. So a couple different summary or upshot of this. Because these were flying at between 500 and 1,000 meters above the objects, little uncertainties inside of the UAVs were critically important. So what you see on the left is small little biases that were actually in the gimbal, primarily for mounting offsets and so on. So if you didn't take those into account, of course, you had big problems in just trying to estimate the location of what the object was. So what you'd like to do, again, is estimate all those locally, process all that information locally, but then only send information across the network that is relevant to the tracking problem. And so we were able to do that. The nice part about this is it really reduces communication and computation. So we weren't sending pixels or anything like that across. We were sending just very basic information of the location of the object and the uncertainty associated with that the UAV had been collected locally. So the nice part about this is, even though we were doing this and marginalizing local information, in this particular problem, the decentralized version was nearly identical. You do lose something by marginalizing this local information, but because it wasn't a major part of the problem, it's really just averages some uncertainty, discounts the information as you're sending it. So the next thing I'm going to talk a little bit about is what happens when you go to non-Gaussian distribution. So instead of tracking, let's say, a point object on the ground, which you can represent nicely as a Gaussian distribution, what happens if you have non-Gaussian distribution? So there's a bunch of different examples here. Occupancy grid, of course, is one, but data association and tracking, search problems, for instance, and then even semantic information. So what you can do is you can write out the DDF or distributed data fusion equations using general distributions. Okay, what you'd like to do is you'd like to model the sensor likelihoods, even if they're not Gaussian, and one of the representations that allow you to do that might be Gaussian mixtures or particles. And then you apply the prediction and update equation. So in the general form, it looks something like this, where the fused distribution is the two local updated distributions. So I collect my local information, I fuse again, and then I put them together, and then I subtract out the common information, which in this case is dividing by that common information distribution. So you're able to write out all the equations in exactly the same way. The key problem now, though, is that now you're going to particles and Gaussian mixtures, and it becomes more difficult to figure out how to develop recursive solutions in closed form. So we've developed a couple of different ways to do that, typically using particles and Gaussian mixtures. And I won't go into too many details on it, but I will talk a little bit about some of the applications. So one application that we focused on is actually taking this all the way to using human semantic information. So this is one example where if you have some type of prior likelihood on the right, a human can communicate with natural information, for instance, and say something like, no one is near A or someone is near B. Okay? So what that allows you to do is what we can do is we can create likelihood models, typically with, again, Gaussian mixtures or particles, that allows us to capture that piece of information, fuse it with the distribution on the left, and then you get the posterior that's sitting on the right. So somebody is near B is given on the bottom right. That is typically what we call positive information. Okay, so it's a positive detection and things like that. But just as informative, what we found in a lot of our experiments is negative information, which is nobody is near A. So what that does is effectively it carves out part of the space, of the search space, where their objects might not be. Okay. So what we found is when we started doing human and robot testing, it was very, the use of negative information was very well used by people. So this is an example of a human search application. And what we did is we had 5 people, and what we wanted to do is we wanted them to search. And we tried to do this, my challenge to my students at the time was to try to do the DDF methodology, but just with humans, using the search problem. So the model is a probabilistic graph of the model of the sensor itself is all the way on the left-hand side. So each of the people, which were my students, basically had GPS. They also had helmets on, so we knew which way they were looking. And then what we did is we collected data on the likelihood of how easy they could actually detect objects. So for instance, what we did is we would put an object on the ground, have them close their eyes and open their eyes, and if they detected something, that was a positive detection. And so we developed a likelihood, and exactly intuitively what you would think, which is on the periphery it started to drop off, and then in the range it started to drop off as well. So this is a playback of the data shown in different forms. This was a sort of a half a kilometer grid on the Cornell campus, and they were searching for small green eggs in the middle of the summer. I always find the bottom right movie to be the most insightful. So we didn't tell the people where to go, but they had the PDF with them. And so they could talk and divide up the space on what they would want to do. The dashed lines mean they weren't communicating, and so they could only communicate when they actually came back together. This was all done with grid-based, but it was formally exactly the DDF methodology that all the way just done with humans. You see sort of there's a big uncertainty growing in this case, and this is when somebody walked right by a building, effectively their GPS went away, and then there weren't any localization measurements of where the object may be, or where the sensor may be. So you can imagine in the sensor methodology in this case, that person might be saying, yes, I found something, but they don't know where they are in the world. And so in that case, the sensor starts to break down. So it was pretty insightful. A couple of the key challenges that we found here was the constraint of the tree topology. So people would come back and try to talk, but their data would not be connected because we had set up a static network as we started moving along. So that was one of the biggest aspects.
So do they all have the same PDF? The one on the bottom?
They initialized with the same PDF, but as they went away, they had different PDFs.
When they communicated, they sync back up.
When they communicated, they went back, yeah. And because this is we'll talk about that in just a minute, but because it's a static process in terms of we're just looking for things on the ground that aren't moving, the fact that there were delays and everything like that, as long as you come back and communicate, you're going to converge to the same estimate. So that's sort of lead into the final topic I'll talk about, which is network complexity, really focused on delays and drops and topologies. So this is a plot of going back to the collaborative mapping problem. And what we were able to do is we were able to simulate different kinds of things in the network. And so there's a bunch of things going on in here where there would be comm failures, which is shown in red here, and portions of the time when robots were collecting information locally, but then not communicating, and then so on. The key aspect of this is because it was a static process, that means we're just trying to map something and nothing was moving and everything like that. The prediction equation, if you want to think of it that way, if you're an estimation person, is very simple. It's static, so you're just collecting information. So the fact that there was a failure or a drop of packet doesn't really matter. As long as you can communicate at the very end, you're going to always converge to 100% information, the same information. So effectively, static processes are a little bit robust itself to the network topology, which is really, really nice. One aspect of the mapping problem, the collaborative mapping problem, that is interesting is that topology is important for speed of response. So these are a couple of different examples in terms of there's a bridge topology here and a chain topology. And the chain topology typically takes a lot longer in terms of the speed of collection of information. And the key aspect of there is that the speed of your response is directly a function of sort of the end-to-end size of your network. So, but the big challenge is what happens if you have more complex processes. So for instance, tracking objects on the ground and those types of things. So this is, in this case, the prediction equation becomes much more challenging. So if you want to think of it this way, each of the different nodes is trying to do its own prediction equation and then update. And so that creates, if you're not talking, that creates correlations in the data. Or correlations that are really hard to unravel over time. So if I do a prediction update over tens of seconds, and my neighbor does the same thing, bringing those together is not as simple as just fusing it together because we've both done the prediction of where we think the object may move or how its state may evolve. So there's one way of doing this, which is that if you happen to have knowledge of the other agent's actions. In the UAV case, we actually had this because they were each orbiting at a certain elevation. So during that, what you can do is you can actually predict the information matrices. So this is sort of given in the I-hat here. Prediction of the information matrices. This is the prediction of the uncertainty of what the measurement may be. Okay. So in the case of linear measurements, it's actually known as a constant matrix, so it's very easy to figure out. But in the case of nonlinear or with gaseous mixtures, it's a much more challenging problem. So you can do it in this case. I think for the problem, for instance, that Gaurav talked about, it's much more difficult because what happens in the underwater problem is that if you don't talk for a while, there may be some local information collected that causes you to change your plan, and that becomes a bit more of a challenge. So in this case, in the cooperative geolocation problem, this plot is a plot of the steady-state KL divergence, which is a comparison of distributions as a function of drop probability. So the KL divergence, this is a comparison of if there was no drops whatsoever. Okay? So basically 0 is all the way down to the left. Okay? So if so the drop probability means that I'm dropping 50, 60, 70% of the packets. So the dashed line, which is the top, is that I drop the packet and then I never consider it again. So you're losing information in that case. So that bounds it on one side. The bottom line, which is in blue, you store all the information and then you just burst it at the very, very end during a blackout. That is the best you can do, but it's a linear increase in communication and data and computation. So the predicted information, though, what you do is you store all the information, you roll up all the information and send it across. And the nice part about this is that you can get good performance all the way out to almost 80% of drop packets. Okay, so the last thing I was going to talk about is what happens if the network topology you don't really understand. And so there's different ways of actually doing this. So you actually have to start sacrificing something about the approach and there's different methodologies for dealing with this, so I'll sort of go you through this. So the last application that we worked on was human-robot fusion, working with ad hoc networks. So this is starting to put all these pieces together. So we have humans communicating both with tablets and their words, and then we have robots that's collecting laser data as well as detections with vision. And so the nice part about this is we were able to do communications with all these networks across the network, even though it was ad hoc and moving back and forth and so on. So these are just different views from the 6 different robots that were actually driving around during the same kind of search experiment that we were doing previously. Okay, so just a couple more slides that I'm going to focus on in terms of the resilient autonomy. So in summary, this is sort of where I think we are in terms of sensor networks. We can actually solve many of these problems individually, and I've kind of touched on a lot of those. The key challenge, I think, is when you start to put these things together. And that last problem, I actually showed you a couple of different things, non-Gaussian distributions and ad hoc and so on. There's other challenges, of course. There's data is becoming more, or there's more and more data, especially streaming data. Ad hoc networks is really important in the complexity of the process, and certainly heterogeneity is something we're going to talk about today. So in terms of the impact of resilient autonomy, this is just sort of my view of things. The characteristics, I think, of resilient autonomy are robust long-term operations, hopefully improving performance over time, and then reliability in the presence of uncertainties. So here's what I think are the key challenges, at least in relationship to the sensor network problem that I'm aware of. Inconsistencies in the information across the team. So what happens if you have 10 team members and they have different kinds of information? The second bullet then is how do you do distributed decision making in the presence of that? Reliable and predictable degradation in blackouts. So if you actually have communication problems, you don't want to just completely fail. You want it to be able to still operate. At worst case, as a collection of single agents. And then I think learning is going to be critically important and data-driven, but we need principled approaches for actually doing that. So my last slide, I think ideally we try to address these challenges directly, which is basically bringing the theories of distributed estimation and distributed planning together. But then you have to ask yourself, is global consistency, that might be a nice goal, but is it required for every application that you're able to do it? And it's very, very challenging, especially for things like the underwater problem that Earl talked about. I think this work, one of the great things I think about this workshop is thinking about the positive elements of the distributed problem. Heterogeneity is one. For instance, if you have cloud and agents, you could actually distribute what the processing is and what the functionality is, which is really good, as well as make sure global decisions. And so the final 2 points, really the first one focuses on learning methods. I mean, I'm a proponent of learning methods, and I think they're really great, but I think they really have to be principled and coupled in with the things that we're already kind of doing, especially with things like the DDF paradigm. And then I think natural and scalable collaborations with humans. I think too often with autonomy, I think this is getting better and better over the past years, but too often with autonomy, there's just a separation between humans and autonomy. And I think to really get the most out of these things, there has to be, the humans have to be part of the heterogeneous team. So that's it.
Thank you.